Lesson 5-4, complex numbers. This is part 2. So we're going to focus today on performing operations with complex numbers. So a complex number has a real part and an imaginary part, and they're in the form a plus bi. The real part comes first and the imaginary part comes second. So in this equation, we want to find the values of x and y that make it true, and we've got a complex number equal to another complex number. And so I'm going to underline the real parts here in blue. 2x minus 3 is the real part on the left side, and positive 3 over here is the real part on the right side. Now, these have to equal each other if the left side and the right side are the same complex number. So let's start by setting the real parts equal. 2x minus 3 equals 3. You can add 3 on each side. 2x equals 6. Divide that by 2. And x equals 3. All right, we solved that. Now in red, I'm going to underline the imaginary parts. The imaginary parts are the parts of the equation that have I in them. So y minus 4 times I has to equal 2i on this side. So we set them equal to each other. Y minus 4 I has to equal 2i. Now I can divide both sides by I and cancel out the i's. So what's really going on here is that y minus 4 has to equal 2. So I'm going to add 4 on each side, and y must be 6. Okay, so it's a pretty intimidating equation to begin with, but if you can pick out the real parts and the imaginary parts, you just set them equal to each other and figure out what the missing variable is. Let me show you another example. So in this one, the equation's a little longer here, but we can still figure it out. So I'm going to use purple this time for the real part. So the real part would be 5x plus 1 on the left and 2x minus 2 on the right. Let's set those equal to each other and figure out what x is. So 5x plus 1 has to equal 2x minus 2. Now all we have to do is get the x's together, so I'm going to subtract 2x on each side. 5 minus 2 gives me 3x plus 1 equals negative 2. I'm going to subtract 1 on each side to get 3x equals negative 3. And then divide both sides by 3. X must be negative 1. Okay, so that takes care of x, and now I need to figure out what the y value is. The y variable here is a part of the imaginary part of our equation. So this part here, 3 plus 2y, has to equal y minus 6. Now, I know that both of them have i's with them, or the imaginary part there, but we're just not going to use that here. For these two sides to be equal, 3 plus 2y has to be equal to y minus 6. So I'm going to take away y from each side. 2 minus 1 leaves me with 1y, so 3 plus y equals negative 6. Subtract 3 from both sides, and y equals negative 9. Okay, that's all there is to it. In this example, we're going to work on adding and subtracting complex numbers. Now, to add and subtract complex numbers, again, you want to kind of match their parts. So I want to, in this first example, we're adding. I want to add the real parts together. 6 plus 1 gives me 7. And then I want to add the imaginary parts together. Negative 4i plus 3i gives me negative 1i, or minus I. And then that's your answer. You have the real part, the imaginary part. They don't go together, so you keep them as two separate terms here. The answer would be 7 minus I. Sorry, I kind of covered that up. 7 minus I. Okay, now part B, we're subtracting, so we have to keep that straight. We're subtracting this time. Again, you only want to subtract or add, the parts that go together. In other words, it's kind of like adding or subtracting like terms here. So we're going to take 3 minus 5. Those are the real parts. 3 minus 5 is negative 2. And then I have negative 2i minus negative 4i. Negative 2i minus negative 4. There's a double negative, so it's really like negative 2 plus 4, and we get positive 2i for negative 2i minus 4, negative 4i. And again, that's your answer. You've got it in kind of our standard form here, the a plus bi, or the real part plus the imaginary part. Okay, the next one we're going to multiply. So we've learned how to add, subtract. Now we're going to multiply. And to multiply these, you can think of these as binomials. We're going to use FOIL. There's kind of one key difference and it happens at the very end. So let me show you how to do it. So foiling or using the distributive property, we're going to take 1 times 7, that's 7. Then 1 times negative 5i, that's minus 5i. Then 3i times 7, that's plus 21i. And then 3i times negative 5i gives me negative 15i squared. Okay, so I can put together like terms here. The i's in the middle go together. So I've got 7, this is negative 5 plus 21, so that gives me positive 16i. And then I've got this minus 15i squared. But remember, we have to kind of think back here. I squared is defined as negative 1. So I'm going to make a substitution here. Instead of using I squared, I'm going to fill in negative 1. Now there's no more imaginary part here. I squared is negative 1, so we make that substitution. I can multiply these together and continue to simplify. So 7 plus 16i, this will become plus 15, really equals, I'm going to put together my real numbers, 22 plus 16i. And again, you want to make it in this order so that the real part is first and the imaginary part is second, so that it's in kind of that standard form a plus bi. So 22 plus 16i. When you multiply or add or subtract or whatever, when you do these operations with two complex numbers, you're going to get a complex number as your answer with a real part and an imaginary part most of the time, unless they, unless an imaginary number would cancel out. Okay, last kind of concept here. Complex conjugates. These are two complex numbers that are in the form a plus bi and a minus bi. So the first number is the same, the real number is the same, and then the imaginary parts are opposites. You're going to have a plus bi and a minus bi. There's something kind of interesting that happens when you FOIL these. Let me just show you real quick here. So if I multiply these together, these complex conjugates, a times a gives me a squared. A times negative bi is minus abi. Bi times a is positive abi. And then bi times negative bi is minus b squared I squared. Okay, so putting together like terms here, negative abi and positive abi cancel out. And I have a squared minus b squared, and then we're going to make the substitution here. I squared should always be turned into negative 1. So I squared becomes negative 1. And now what I really have is a squared plus b squared. This is kind of a formula here, an identity. Anytime you multiply complex conjugates in the form a plus bi times a minus bi, you always end up with a squared, the first number squared, plus b squared, the second number squared. We can use this idea to help us simplify fractions, and that's our last example. So we want to simplify this fraction 3i over 2 plus 4i. In other words, this is a division problem, but we want our answer kind of in a simpler form. Basically, we want to divide these two complex numbers and get another complex number. So how can I simplify this into just one complex number? Let me show you. So what we do is we want to really eliminate the denominator here and get rid of any imaginary part in the denominator. So I've got the complex number 2 plus 4i. I can kind of cancel out that denominator, simplify that denominator by multiplying top and bottom by the complex conjugate. And the complex conjugate of 2 plus 4i is 2 minus 4i. All you do is switch that middle sign. And I need to multiply the top and bottom by the same number, so that what I'm really doing is just multiplying the fraction by 1. Because when you take something over itself, the fraction really is just 1 over 1. Okay, so I'm keeping everything equivalent here. I'm not really changing the problem. I'm multiplying by 1. All right, so on the top, I'm going to distribute 3i, and I get 3i times 2 is 6i minus 3i times 4i is 12i squared. And I'll change that later into -1. In the denominator, I'm going to FOIL this one here, but just so you know, you can use the shortcut or the trick that I just showed you. 2 times 2 is 4. 2 times -4i is -8i. 4i times 2 is +8i. And then 4i times -4i is -16i squared. So let's see what happens in the end here with our denominator. The -8i and +8i cancel out. And now I'm going to change my I squareds into -1. So on the top of the fraction, I've got 6i minus 12 times -1 because I squared was -1. And then in the denominator, I have 4 minus 16 times -1. I squared again becomes -1. Okay, so then multiplying these negatives here, we get 6i plus 12 over 4 plus 16, or 20. 6i plus 12 over 20. Now, I want to put my answer in standard form for a complex number here. So a plus bi, a real part plus an imaginary part. So my real part comes from this part of the fraction, 12 over 20. 12 over 20. Well, let's reduce that. 4 goes into each number, so I get 3/5. That's the real part. 12 over 20 is 3/5. And then my imaginary part is 6i over 20. And if I reduce that, 2 goes into each number, I get 3/10 I. Positive 3/10 I. So we want to simplify the fraction by eliminating I in the denominator. Notice I got the just a whole number 20 here, a real number 20. And then you can simplify your fraction into a real part plus an imaginary part. So we've got the complex number 3/5 plus 3/10 I for our answer. Okay, finally, I want you to try these two on your own. So the first one you're going to multiply using FOIL. And then number 2, I want you to simplify the fraction like I just did the last example.